All right. So just a little bit of background, how we're able to offer this training today for you and for free. So 3CREN, or the Tri-County Regional Energy Network, we are a collaborative partnership between San Luis Obispo, Santa Barbara, and Ventura counties here on the Central Coast. And our mission is to improve energy efficiency in our region by offering free programs and services for building professionals and households. We are funded by ratepayer dollars that we all already pay into our utility bills through the public goods charge. So benefit of that being ratepayer funded is that there is no cost to those that we are able to serve. And as a regional energy network, there are a few others around California, but as a regional energy network, we get to return some of these dollars back to our local area, which historically on a statewide level has not benefited as much from these funds. Awesome. Next slide, Albert. We're actually back at the beginning.
Oh,
so
sorry, there we go.
Perfect. And you can hop one more even. Perfect. So we do have 3 programs that we offer. 3CREN, Energy Code Connect is one of them. So primarily serving building professionals by offering services for plans examiners, inspectors, and architects for residential and non-residential applications about the Energy Code or Title 24. So we have trainings and resources. We offer regional forums, which kind of convene energy code issues as well as policy or other technical issues. And we also offer Energy Code Coach, which is a resource for y'all if you do have specific questions about the energy code. We have experts who work with us and are able to answer some of your questions, offer guidance, or point you to the right resources. Next slide. We also offer our building performance training program, which again primarily kind of focuses on some training, education, instruction, pointing you to resources. We're really focused on developing technical skills for our building industry professionals, but also soft skills. So marketing and communication techniques about some of the great technologies or skills that you offer. For example, we offered a passive house tradesperson certification actually last week, and we covered that cost completely for our participants. We also offer some real estate certifications like the Green designation through the National Association of Realtors, and we'll be doing some BPI certifications in the coming year. Finally, perfect. Yeah, next slide. Our home energy savings program is really ramped up in the last year here. We have our multifamily program and our single family program. And we're offering incentives to property owners for our multifamily program to do comprehensive energy upgrades. And through our single family program, we're connecting you with contractors who are able to offer additional incentives and pass on savings to customers through metered energy savings. As well, for each residential project through our single family program, right now we do have $1,000 of upfront bonus payments. So we do encourage contractors to take a look at that and sign up if relevant. Awesome. Next slide. I think this might be my last here, but if there are any other 3CREN staff on the call, you can look out, may have a background similar to mine or the one on the screen. Feel free to chat us or myself any questions during today's presentation. I'll be happy to help. All right. And with that, I want to hand the presentation back to our instructor today, Albert Rooks with Small Planet Supply. So thank you so much for joining us, Albert, and looking forward to learning a bit more about ventilation and passive house today.
Great. Well, thanks much, Sean. Good morning, everyone. I'm super happy to be here. A little bit about myself. I am the CEO and founder of Small Planet Supply. Small Planet Supply was really an output of organizing Passive House Northwest back in 2000, 2008, 2009, really became active in 2010. And working on Passive House buildings, large and small, has been a really, really interesting journey here in the US and in Canada. I'm actually beaming in today from Richmond, British Columbia, in a water heating facility that we set up here recently. Ventilation is a really fun topic. We'll dive into that here in a moment. First, we just, kind of want to understand who's with us today. Chime in on the, kind of what your position in the industry is: builder, designer, professional. Oh, and there's a poll, how handy. Now we can just kind of select that and move in. I'll just give a moment to get some data in there, and then we'll move to the next one. And there is the next one. And where everyone is located today: Central Coast, elsewhere, United States, Canada. Oftentimes, it's surprising. The Passive House world is very interconnected, and the knowledge exists across the North America continent, and it's interesting to find out where everyone is. And then lastly is how familiar you are with Passive House. It's a new thing. You've had some experience, and there are those that work exclusively in Passive House in every project they design or every project they build, and it's been that way for a number of years. Let me know when we should jump ahead there, Sean.
Absolutely. I'll give it 5 more seconds. There it is. I'll go ahead and close it. Could share some of the results.
Great. Great. Lots of folks from the design community, which is great because it's super important to catch these projects early in the stages to really think about the ventilation design. So we'll keep talking about that and plenty in the other category. Great, thanks. I will close that on my end. So let's go ahead and dive into Passive House ventilation. So I always love looking at this slide. It appeals to the nerd in all of us, but it's actually true. There's a lot going on in Passive House ventilation. It's accounting for a lot of different things going on within the building. And in a Passive House, we know the building envelope has to go through the 0.6 ACH 50 air tightness goal. So everything that happens within that building envelope really, really matters. And so it has to do with what the occupancy is, how much CO2 the occupants are producing. We've got to manage smells and other air quality issues. And then along with that, we're really accounting for the gains and losses of energy. And human respiration is actually a gain. It's an output of BTUs and affects the heat load of the house. So the general rule is it's really about comfort and health first. Then it's really taking those comfort and health standards and then seeking the lowest energy penalty to accomplish those standards. So it's not totally about energy, comfort and health first, and then energy. So just stepping back to the basics of why we want to ventilate a building is, again, in Passive House buildings, we've got these really super good air barriers. Took a tour of a building in Vancouver, BC last night. I think it was a multifamily building, 57 units, probably about 6 floors, and it's slated for occupancy today. And the air barrier was intact. the ventilation rate, I'm sorry, the air leakage rate was 0.48 ACH on a big building, which is super good. Big buildings are a little easier on air barriers than small buildings, but still, that's just a phenomenal number. So within that air barrier, we're going to provide some occupancy, and that occupancy is going to create some respiration, which is going to put out a lot of CO2. So we've got to replace that CO2 with fresh oxygen. At the same time, it's going to create a lot of water vapor. Depending on what climate we're in, water vapor is going to be a thing to manage. And then VOCs are always going to be a thing to manage. So the ventilation is going to create the safe haven for people to exist and live in the buildings. And at the same time, because we have to replace that fresh air, take out the CO2 and replace it with fresh air, we're going to bring in unconditioned air to do that. And so that's where we begin to seek the lowest energy penalty for doing those air exchangers. Along with that, the air, certainly in California, we've got new filtration requirements coming on right now, which are MERV 13 and more filtration required, still kind of catching up on what the next benchmarks are. Then do we need to temper the air? Do we want to temper the air to provide some cooling? How we're going to manage humidity, and how we can accomplish the heat recovery, and whether we're in a heating climate or a cooling climate, and whether that the recovery device needs to manage moisture or enthalpy also. So relatively simple topics, but they're all important topics to address. And as we address them, we want to stay in this kind of that gray zone in the middle. And the gray zone is really looking at indoor relative humidity. So there's a set of brackets anywhere above 30% up to 70% relative humidity is considered pretty comfortable. The sweet spot's right there in the middle, right around 50 to 60% relative humidity. And so that can be a challenge. You know, if we put a building up in Tahoe in the winter and we need to give it 0.3 air changes an hour based on standard residential occupancy, that building, if we're not careful, that building's going to dry out depending on the occupancy load. We take that same building and we put it right on the coast, on the Central Coast in California. I regularly see dew points on the Central Coast in the middle of summer in the mid-50s, which if we bring all that air in, it's going to create a pretty high humidity level inside the house. And so we want to think about regulating that both in summer and in winter. So all these conditions are a little different depending on where you are in the state or where you are in the world. And the ventilation design is designed to handle that. It's not terribly difficult. We just got to think about it a little bit. So we want to maintain these safe levels between 30 and maybe 60 to 70%. Any higher than 70%, we can see in the second paragraph, we've got a risk of mold and other things that the human body doesn't really like. And if we can keep it within that 35 to 60, that's where the occupants are going to be the healthiest. There we go. So getting into design and ventilation requirements, and beginning to look at the equipment. So essentially, as we create a passive house, we've got this great air barrier, and the windows are operable. There's no restrictions around that. But literally, for the occupants inside, the ventilation system, HRV or ERV, in a passive house, it's always going to be some kind of an HRV or ERV. We'll get into kind of what the minimum thresholds are, but that's really the lungs of the house. That's really how the house is going to operate, or how the living environment is going to operate. Same thing for commercial spaces, same thing for a fire hall, same thing in a school. It's really the lungs and how we're going to control a healthy environment. And the way we're going to do that is really quite simple. We'll look at a design, we'll set a unit in, and we'll start by establishing an overall airflow rate. There's a couple of slides later that will look at those overall rates. But once we establish those rates, like in a single family home, that's about 2,500 square feet, right? Kind of that classic example. The standard ventilation rate is going to be about a 0.32 air change per hour rate, which will turn out to be right about 110 to 115 CFM. And when we look at those standard homes, it doesn't really matter if it has a cathedral ceiling or anything like that, because the air exchange rate is really based on to serve an occupancy load. And there's kind of three ways we design this. So we'll assume the first 8.2 feet of volume to establish that ventilation rate. So we'll kind of ignore high ceilings and things like that, because it's really, you know, kind of volume per occupancy rather than total overall volume. So anyway, once we establish those rates, we're going to bring fresh air in, and we're going to pipe that fresh air because we have a certain budget, and we're going to pipe it into the bedrooms. So the green plus signs are the supply zones. So we'll supply fresh air into the bedrooms and maybe the living room as a secondary measure. And then those are positive pressure zones, if you will. And then the red areas are the exhaust locations. So we'll always be pulling out a minimum of 20 CFM per bath, and another 20 to 30 to 36, depending on the condition in the kitchen. So the way this works is we supply, or we pressurize living rooms and bedrooms, and that pressure is going to get pulled over to the negative pressure zones of kitchens and baths. And so it'll go over the crossover zones. And we have a lot of crossover zones: front entryways, hallways, any kind of communal space. And the funny thing about airflow in a passive house, more than a standard code house, a passive house, part of their requirement is that all the surfaces are within 1 or 2 degrees of each other. And when the surfaces, ceilings, floors, walls, everything, even windows to a large extent, when you're in that condition, the air kind of mixes. It's not forced into hot air rising and air turning in that method. If you start pumping air into one of these environments and all the surfaces have a very, very similar surface temperature, then the air is allowed to move just by its own flow and not really affected by the driving forces of surface temperature differential. So interesting stuff. So essentially, fresh air, positive pressure points, return air, negative pressure points. We supply to positive, it gets pulled out of negative, and then goes back to the unit, goes through the heat recovery stage, and then back outside of the building. When we design those, and as we start getting into what the passive house flow requirements are, we've got to be mindful that across all of the areas that we work in, there's an evolving set of building requirements. And in California, in certain buildings, the conditions may be a little bit different. So we always have to kind of have 2 sets of rules to be aware of. And we want to make sure that we stay in line with local building regulations, because sometimes there's a conflict, and passive house ventilation conflicts with ASHRAE 92.2. But there's a way to harmonize these things and look at them and choose a safe set, because more airflow is generally good, and the downside of more airflow is drying out a building or just wasting a little bit of energy, just due to the losses of higher volume. And too little airflow is also a problem. So there's a sweet spot, and the sweet spots generally align with building regulations, except when you get into funny things about kitchen ventilation and things like that, which we'll look at. And so when we look at on the passive house design side, when we look at ventilation, we can look at it naturally in cubic meter per hour or CFM. But essentially, there's 3 ways that we're going to look at it. 1, total supply. And generally, we're going to want 18 CFM per person on occupant load. So if we consider the 2,500 square foot house, we could call that an occupant load of 4, we could call it 5, we can plug in a different number. That's always going to change, and it could change over time. So the second way we're going to look at it is exhaust rate, because that's pretty reliable. And we'll find in North America that we always typically have more exhaust because we have more homes with multiple bathrooms, washrooms, if we're in Canada. And those washrooms or bathrooms are always going to want a minimum of 20 CFM exhaust rate. In passive house, it bumps it up to 24 CFM. Codes are typically 20, passive house 24. It's a little adjustable. And then kitchens are more in the 36 CFM range. And we'll find that in North America, because we have more exhaust locations, more baths, the exhaust rates are higher than the supply rates. So our exhaust rates are typically higher than our occupancy-based supply rates. And so those will usually take precedent, and that'll be the number that we'll be working for. And typically that aligns well with code and ASHRAE because code's a little bit less. We might see a slide that kind of equates 2 houses with a code minimum rate right now. And then the last thing is kind of a catch-all also. These are kind of 3 safety factors that we align and then choose some values to make our design on, which is the minimum overall enclosure exchange rate. So what we don't want to do is have a super big home. So I've seen, the classic home of 5,000 square feet, up in a high altitude, beautiful home, and it's really built for a couple of occupants. So what'll happen in that is if we look at occupancy supply, it could be 5,000 square feet and 2 bedrooms. Those homes exist, which on a supply side, it's not much flow, but it may have a number of baths and laundry room and kitchen and so forth. So that'll get us some flow. But then again, we need to assume that at some point there's going to be higher occupancy in that building. And so we'll apply the 0.3 air change rate on that 5,000 square feet. And while we might get a very low supply number, we'll probably get a reasonable exhaust number or return number. But the 0.3 ACH on a 5,000 square foot home is going to be, in the 150 to 180 CFM range. And so that'll prevent us from designing a structure that may have higher occupancy just on the supply rates. So it's also worth noting that little thing in red where it says boost speed. Depending on the software that we're using, whether we're using the PHI method or the FIAS method, on the PHI method, which I seem to work with quite a bit, it's just worth noting that these are the boost rates that we're entering in the modeling software, which are really different than the commissioning rates that we would show a building official or that we would balance to at the end of the project. So as you get into the modeling, there's kind of a difference between are you entering in values on a boost rate or are you entering in at the normal rate? And because the model is the modeling software, whether it's Woofy Passive or the PHPP, is really going to look at the ventilation unit, the amount of flow in the climate, and apply an energy loss based on flow and effectiveness or efficiency of the unit. And then that's how it's going to kind of get you right into that really super fine energy balance. Because again, we're creating a building that is living on a very, very fine energy balance, right? We're trying to balance the gains and losses of the building with passive house. And the ventilation losses can be really significant and really drive the building. It's common for me to see in kind of more the Washington, Oregon climate to look at the difference of 10% in HRV effectiveness, HRV territory more in Washington and Oregon, and see the difference of 10% in a 2,500 square foot home is literally the same as 2 inches of rigid foam around the house. Those are the loss equators. So you can see that if you gain 10% in ventilation efficiency, then you will really save a lot of energy. So we'll move along. We've kind of covered this already. We're looking at kind of equations. The last thing we're looking at here is how to calculate the volume and what the effectiveness of that is on the number 3 minimum exchange rate. So as we come out of this, we're going to wind up looking at these supply rates here of 90 cubic meters per hour. We'll look at an extract rate and get around 120 or 72 CFM total down there, and then the minimum exchange rate is 52 CFM. So we've got some wildly different numbers, and really the numbers that'll stand out in cubic meter, pardon the cubic meter, is the supply is low. The air exchange rate in this case is low, 87.7, but the extract due to the kitchens and baths jump out at 120. So we'll really carry forward a design based on 120 because we really need to satisfy all these, and a little extra supply is not a penalty, and a little extra supply from the volume-based calculation is not really a penalty also. So we'll go ahead with a 72 CFM on this, and it's apartment, 3 people, 1 kitchen, one full bath, and one water closet. So so as we move forward, I'll just kind of close up on this. The supply rates matter. Passive House calculates it a little bit differently. We want to make sure we're within reasonable guidelines on supply, extract, and the volumetric calculation, and then also make sure it applies to code. Generally, what we'll see in Californian single-family residences, as well as multifamily residences, the code minimum are pretty low rates. They're more in the supply rate zones rather than the exhaust rate zones that we'd see in this particular case. So generally that'll come out pretty safe. So now let's actually move to on the equipment side and see how these things work. So HRVs or ERVs, we'll talk about the difference between the two. And on the left-hand side of the screen, we can see the outside connections, right? So blue just maybe means it's cold. So we've got some air coming in. It crosses the core there in the middle and then pops out in our lower right-hand red arrow, and that would go into the supply zones of bedrooms, living room, etc. And then we pick up all the return air from kitchens and baths. It would show up in the unit in the upper right-hand red arrow and then cross over that core and then bring the and then exhaust out. And so what we're looking for ideally in equipment is, pretend it's, we've got it 70 degrees inside and it's freezing outside. So real simple calculation, 32 outside. So upper left, we've got 32 degree air coming in, but our building is conditioned to 70 degrees Fahrenheit. And we've always got to give it a little bit of heat, right? It's always a case when it's cold outside, we need a little bit of heat in the building to maintain that temperature and comfort zone. So we've got 70 degree air coming back upper right. And so the transaction we're looking for is we bring the 70 air in, we bring the 32 air in from upper left, we cross them over in the core, and we strip off the energy of the upper right return flow and redirect it down into the lower right supply flow, keeping the energy inside of our thermal enclosure. That's the transaction that we're looking for. And there's different ways of calculating it, but essentially consider this: the HRV or the ERV is part of the building envelope. It's a thermal boundary. It's just a thermal boundary that allows air to pass through it. So like all thermal boundaries, the more efficient and the least loss that we can deploy means the least amount of energy leaving our building in cold conditions or entering our buildings in warm or hot conditions. So fresh air from the outside, return air on the inside. We go through a heat recovery core. We look for that transaction, and we send out as cold as possible flow out the exhaust, lower left, and we warm the incoming fresh air in a cold condition as much as possible on the inside. And that's it. There's nothing else going on. There's no heat pumps. There's no other activity other than 2 fans and some kind of thermal recovery device. There are various kinds, but the most common are a flat plate heat exchanger of various materials, and we'll kind of get into why. But the shape really matters. So that shape in the center, in the middle of my yellow X, sorry about that, is the common shape. It's a square tilted on its corner. And that's about as bad as you can get. These are the good ones. We look at the right hand, that's my square tilted on the corner. And really all we can get out of that is 40 or 60% recovery. And we look at the extreme left, and it's a really elongated, it's kind of like an elongated square. And the one in the middle is the most common, a counterflow core. And it's that square that's just been elongated. Because if you think about it, what's happening in the worst performing one, the 40 to 60%, is we've got warm airflow approaching upper right-hand side, and then an opposite flow coming on the opposite side. And they've only got a little bit of room to meet and do a heat exchange. And because it's a short duration where the flows are in proximity with each other, there's a relatively short possibility of doing a heat exchange. But if we make that channel longer, we increase the duration of time that the 2 flows of the temperature extremes are adjacent to each other. And that just causes a longer or more heat to be exchanged. If you consider it this way, it's a super difficult topic to get, but warm air enters the core. Sorry about that. Warm air enters the core on one side. Cold air enters the core on the other side. So they're both flowing at a constant rate. And so the warm air, when it enters, immediately it starts cooling a little bit. And that heat shows up on the track that's the cold air entering. Then it goes a little bit farther, it cools a little more, which means the other side warms a little more. Whoops, sorry about that. And it keeps kind of going on. If you make that longer, then the warm stream keeps cooling and losing heat as it goes, until finally it really loses a lot of heat, because the final end of the transaction is that warm air started warm, but as it starts leaving the core, it's at its coolest point. And so how we get that last little bit of energy off of that flow is that at that point where it's leaving the core, it's bumping into the cold air that is the coldest. So it strips that last remaining heat off of it and leaves maybe just a few percentage points, less than 10%, of warmth traveling outside or heading outside of the core. It's an interesting concept to get. Here it is actually in action in a building. So this is a building in Washington State. I know this building pretty well, and it's a really interesting case. So in looking at this graph, this is after the building was built in the year, sorry, I'm going to say 2014, thanks. And this is April in 2014. The building is newly constructed. It's occupied now, but they have not turned on the heating system. Pretty much a full-on passive house. So the very top line, the black line at the top, is the return flows. The next line down is the supply flows. So the very uppermost line is the flows coming back from kitchens and bathrooms, right? So if our set temperature is right around 70, it would be typically a 70-degree flow, but the heating system's not really turned on right now. So it's living on occupancy gains and solar gains in the condition. And so it's floating, right between 68 and 70. And then the next line down is the supply flows. So after the heat exchange transaction, those are the temperature values of the supply flow air that's showing up in the bedrooms and living rooms and things like that. So those are the inside flows. And what we're looking at is the passive house is working just great. The heating system's on. It's April. The lower lines are the outside ambient temperature, and we can see the middle lowest dip is down to about 42 degrees Fahrenheit or something like that. So it's cold outside, and like springtime, it warms up during the day and gives the building some heat, and then it gets cold outside at night. The upper two lines are just kind of bouncing around in a really comfortable zone. So we're not losing the heat that we're gaining overnight. And then looking at the lower lines, the exhaust is the blue, and then the intake is kind of that red purple at the very bottom. So as we start going across this week, it hits the mid 50s, goes up to the mid 60s, goes down to the mid 50s. And so that's our outside condition. We're running about probably 115 CFM, maybe 120 CFM in this house. And we're maintaining the temperature, and we're not losing it over this design flow or this efficiency on the HRV. And we know we're not losing it because all that fresh air that's coming in when it's 52 degrees is showing up in the supply flows right at the unit. That's where this is measured at about 65 to 66 to 67 degrees. So that means that transaction is working incredibly well. And it's working well to the point that we can see actually something funny going on. So what's the funny thing going on here is that in both interior flows at the top, we can see a little peak. In the first little bit, there's a peak where it goes from 68 up to 70. The next day, there's a funny little peak again. The next day on the 14th, there's a funny little peak. It's a little longer. And then finally on the 17th, there's a big peak. And so in a more interactive setting with more time, I'd ask anyone want to take a guess what that is. It happens daily. It looks to happen in the morning. And it raises the temperature inside the house, and it shows up in the return flow, but then is transacted back over to the supply flow. So it's kept in the building. And so the answer is, if anybody's really interested, it's the morning shower. So the family wakes up, they start showering at the same time. And we think about what happens when we shower. We're dumping a whole bunch of hot water into a washroom or a bathroom. And so that's got continuous exhaust at 20 CFM, maybe 24 CFM, or it's in boost mode, which would take the 20 up to 26 or 28 CFM. And we pick up all that energy in the form of water vapor, and it hits the core, moves over to the supply flow, doesn't leave the building because we don't see those peaks leaving the building. It just shows back up in the building. So the unit is doing a really good job of maintaining the energy within the house, even to the extent that it's showing us the morning shower energy coming out of the hot water tank, and it's retaining that energy inside the building. Incredible how that actually happens. So we'll get into recovery effectiveness, and I will just take a look at the chat and see if I can help with any questions. I manage Pets House, 25-unit multifamily building in Nanaimo on traditional territory of, I'm not going to say the band name correctly, even though I'm over in Richmond. And I don't see a question there unless I missed it. George, the range hood will come in later, and we'll be able to talk about that. And someone's in a 50s vintage home in zone 3C, going from wholly near passive house standard homeowner. Okay, great. So nothing I'm sure that I should respond to at the moment. Any data of CO2 and VOCs in bedrooms? Yeah, actually, I do. There's a slide coming up on that, and we can talk more about that if there's more specific questions. So jumping back to just how the building works. general recovery effectiveness and moisture and humidity, which is also going to kind of help us talk about CO2 a little bit. So in a building, especially with a tight air barrier and a really super good ventilation system, we always make a lot of moisture. So we've got to have a way of managing that moisture, and the moisture load is really dependent on where we are. And so in a passive house planning package, PHPP or WFI passive, essentially we're going to account for all the moisture that we make inside the building. And then we're going to understand how much moisture we lose. And generally, because there's a climate file associated with the project, we'll understand what the moisture conditions, humidity conditions are on the outside of the building. So in the PHPP, these are basically some assumptions that are programmed in. It's already in the algorithm. We're just showing some values, but everything we do creates some level of moisture. And what we don't want to do is create too much moisture or starve the building or the occupants for moisture also. So we'll get into kind of how that works, but it's really very, very situational. There's a map, and maps can give us good guidance, but it's when we get down to it, we have a lot better capability than maps. We've got some things to consider, like the same building, the same 5,000 square foot building, low occupancy in a high altitude is going to be completely different than a 5,000 square foot building, high occupancy in a high altitude or low altitude. Occupancy really matters. Many things about the building really matter. And you really don't judge by a map. You can judge leaky, poorly performing buildings by a map. Generally, in passive houses, the software is really equipped to understand the conditions inside and outside and really give you some good advice. So as we get into how we manage moisture, it's important to understand that the transaction with moisture is exactly the same as the transaction with heat. So on the left-hand side, in the winter, we're taking cold, dry air, typically in a heating climate, if we're up in the Sierras or something like that, or depending on wherever we are, we'll take in cold, dry air, and we'll want to exhaust out cold, dry air. That's what we're looking to do. And then on the right-hand side of the screen, we're going to take in warm, moist air, so to speak, and send that stream outside and turn it into cold, dry air. And the only way we're going to be able to do that is to create a core that can do the same thing with moisture that it does with heat. And so as we do that process, essentially we're going to run two airflows next to each other. We're going to be looking for humidity and heat recovery. And so we're going to use a different style of a plate heat exchanger in most cases, or there's other ways of doing this also. But essentially, we look at the top line, that top kind of green-blue arrow where it says extract from the building. That's airflow with lots of moisture, right? All those little bubbles along that airflow is high moisture content. And then we'll create some kind of a plate that is going to see that heat, and it's going to take that heat because the other side of that plate doesn't have any heat, right? Nature's always going to seek to balance itself, right? So I've got lots of heat, you don't have lots of heat, so it's going to seek equilibrium naturally, and it's going to do the same thing with moisture. So if we create a plate that is kind of moisture, that will transfer moisture through enthalpy, right? Turning it into a vapor, moving the vapor through the medium and having it show up on the other side of the plate because the other side has no water vapor. That is how we're actually going to get the enthalpy recovery to happen. So the two streams never touch each other. The water vapor doesn't touch each other. The water vapor breaks down, wets the surface, transfers through without being a water droplet, if you will, and then shows up on the other side and then gets pushed back inside of the building. So the heat comes from the bath, transfers over the plate, and goes back into the building, and the water vapor comes from the bath, transfers over the plate, and goes back outside of the building. And this is, I'm going to jump back here. If we were in Atlanta, Georgia, right now, or the middle of August or something like that, we would want exactly the same thing. We would do the same appliance, and we would just change that sign to summer. And the extract air, what we'd be looking for is we'd have a building, hopefully with a really good building enclosure, a small amount of cooling, and that cooling will generally dehumidify the building. And then while it's 96 degrees outside or 92 degrees outside, and in a really high humidity factor that hot and humid climates would have, essentially what would happen is the outdoor air would come in, it would be hot and humid, it would hit the colder, drier air on the inside. The cold dry would get redirected across the core back into the building, and the hot humid would get essentially rejected across the core and pushed down the outside of the building. Same device, no programming difference, nothing. It's just the way the physics of the transaction works. The core is always seeking to redirect the high concentration of either heat or enthalpy back in the direction that it came. So interesting stuff, not terribly complicated, but interesting nevertheless. How this all affects the building load. So here is a single family residence in BC, Canada, 0.6 ACH, triple pane windows, 14-inch thick exterior walls, because it's cold up here in Canada, 24-inch thick roof, 14-inch thick sub-slab foam. So this is a full-on passive house. It's been modeled. And now we're going to actually look at the PHPP and see the effect on the heat load of different ventilation devices. So device number one, an ALDS unit. The ALDS unit is essentially 76% effective. In a passive house, the minimum unit you can use to have any certification, at least on the PHI side, is 75%. FIAS has got a different way of looking at it, and that's all fine as long as this equipment meets whatever criteria and whatever design modeling software that it's being applied to. As long as that all works, that's all fine. And we're just going to look at the difference in the units. The next unit right now, okay, so the ALDS is going to give us a total heat demand of 15.7, right? So it's not 15 kilowatt hours per square meter per year, it's 15.7, and that's a no-go, right? So down in the lower right-hand corner, that green square says no, so we are not a passive house at that point. So one of the things we can do is change that 76 to a higher performing unit at 83%. Comfaware 350, I work with these things every day, and they're 83 to 84%. We'll use the 83.1. That's the data that the modeling software provider likes in this case. So we drop that 83% in, and what does that do to the building? It takes the 15.7 down to 15. It puts the building in certification. We haven't changed anything else. So from 76 and change up to 83, those few percentage points put the building back in certification by reducing the heat loss and essentially by reducing the heat loss and reducing the load on the building. So there's one more change that we can make because there are higher effective units. In this time period, we had a Novus 300, that's 92%. Now we've got a new series of Q, which is Zender Q 350, 450, 600 different units. And those range from the 87 to 90, 91% range. So what happens if we put a 92? So we go from 76 up to 92%. And the load drops down to 14 kilowatt hours per square meter per year. So that's an 11% reduction. That is just by making the change in the HRV. Bear in mind, at this point, we've already modeled the building. It's already, and the Canadian climate that it in is like zone 4C. It's not a crazy climate at all. And so the building was modeled with triple pane windows, and a 14-inch thick wall and 14-inch sub-slab foam, and a 24-inch ceiling. I don't know what the values of the 24-inch lid was, but we haven't changed any of that. And to effectively add more insulation on that building or buy better windows or put more sub-slab foam in, that's a big, big expense. And I think we might have spent a couple $1,000, $1,500 by going from Alds up to a Novus 300, maybe $2,500 in order to get that performance for that kind of money with not having to change our building. That's a real significant factor. So what we find is that the ventilation performance levels can really make a building work really quite well. So recovery effectiveness and PHI certification, the little guys are just not suitable. The middle guys are probably just fine. Here's how we actually get to those numbers and how those numbers are put in. In both PHI and FIAS, there's minimum sort of qualifications that you have to have on these units. There's methods of testing. This testing method is basically looking at a unit, running it across the 3 boost loads. And essentially the unit, when you pressurize the unit, it can't leak between the return flow and the supply flow by more than 3%, because something bad will happen that we'll look at here in a little bit. And we've got to test it in cold climates. It's got to be better than 75%. So 3% minimum, 75% outdoor, constant flow rate, and it's got to be less than a 10% imbalance. That kind of shows up at commissioning, but we have to be able to meet those things. It can't consume a lot of energy when it's running, so it's got to be less than 0.45 watts per cubic meter. With the frost protection device, it can't be loud, otherwise nobody's going to want to be in the building with it, right? So it's got to be 35 dB or less, and it's got to have frost protection for most mild climates, and most everything that we see inside of these units are good to minus 15C. So back to the way these things are tested, there's 2 different ways that they're looked at, and it's generally better to look for the most stringent certification and use that in the modeling software, because when you're designing a building that's on such a tight energy balance, you really want all the data to go in the modeling software to be highly accurate. That way, that's the way you're going to get the best results. So here's 2 different methods. PHI essentially looks at the return air pathway as it leaves the building. So we're really mindful of overall the lower left-hand arrow when what temperature the air is leaving the building. The industry, we've had a North American industry here for the last 30 years, coming on 40 years now, making HRVs. They're really quite good. They invented the industry, right? The way that they developed of looking at it is really looking at the outdoor air temperature coming in and how that air shows up across the supply flow. But there's a couple of ways that we don't really pick up all the airs with that testing method. And so we'll see a couple of examples. So those are the calculations of the testing methods. We're essentially looking at air temperatures at various points and how the transaction happens, how they enter, how they leave. And here's an example of the differences between the 2. And this is what we see in the North American equipment literature. The upper red line is the SRE. ASRE is the proper word to use, apparent sensible recovery effectiveness. And so when we look at the unit could be, $1,200, and it's listed at 88% there on the right-hand side. And maybe it is really 88%. It's probably not $1,200 if it's 88%. We'll see another one here shortly. The PHI method looks at the leaving air temperature and compares, and when we look at both of these, essentially we see they're very tight. They're very, very closely aligned. which means that this is a good unit. These 1, 2, 3, 4, 5, 6 units, all those temperature points or effectiveness points are a unit that's actually measured and tested on both sides with both measurement testing. Those are really quite good units because there's not very much of a spread. This is where the data becomes interesting. In the less expensive units, they can show a high effectiveness of 92% listed on the ASRE, the manufacturer's data. But when you apply the PHI method, you find that the effectiveness is much, much lower. And the reason is, I'm going to go back to this transaction right here. There's 3 ways that happened. The PHI method looks at the leaving air in the lower left-hand part of your screen, and the leaving air wants to be as cold as possible. The current North American industry is really looking at the supply flows, and we got cold air coming in and we want to see warm air showing up in the bedrooms. So if we see warm air showing up in the bedrooms, then the unit's probably working and we have a high effectiveness. Unless we have a leaky unit in that the return air coming back from the bath leaks across to the supply flow, and that warms the unit. It's not really a heat exchange, it's leaking air. And we would know that because it's air leakage that's warming the supply flow, and that warm air doesn't really get cooled off by heat exchanger. So as it leaves the building, it looks actually fairly warm. And that's kind of really where we're seeing the difference. The other way that can happen is that the unit is not well insulated and placed inside the thermal comfort zone of the home, right? If we warm the home to 70 and then we place the box that's steel and uninsulated inside of that 70-degree room, then we're just warming the flows that are coming in. That's not really a true heat exchange. So that's kind of some of the ways that we can develop these real big divergent specifications across the units. There are databases that can assure you by various testing forms that the numbers that you're putting in are actually real defensible numbers. And then now we'll move along as we're getting closer to the hour mark. We'll move along to unit placement and duct design. One of the most important things is to think about where the fresh air is coming from. So want to think about sourcing it up off the ground, not in an area where it's going to pick up gases from cars or streets or something like that. So just think about where that is, and also provide some separation. We don't want to pick up the supply air right next to where we dump the exhaust air. HRVs and ERVs. HRVs for sure need a condensate train. Because we're going to take warm moist air back from bathrooms, and we're going to condense that air, and or we're going to cool that air, which is going to condense the water out, and that water needs to be drained out. ERVs don't always have to have a condensate drain. The ERV is transferring the moisture across and giving it back to the supply flow. So it doesn't really need to drain that moisture out. And then the other thing you want to do is think about where you can actually place the unit. Placing the unit as close to the building edge as possible is the best from a performance standpoint, because you think about you're bringing in freezing air from outdoors and you're putting it through an insulated duct. And there's always going to be a loss because it's not a perfect duct, and there's going to be thermal transmission across the duct. So shortening that duct flow will reduce the thermal loss. That's just a simple placement of the HRV. It wants to be in a place where we can get at the filters. Attics aren't great. Basements, crawl spaces aren't great. It wants to really have its own home. And if it's going to be above 76% effectiveness, it's going to be large. Even in a small multifamily, these things take some space because we're essentially trying to do recovery off of airflow. And so we need plate surface area to accomplish that. All the cold air ducts want to be insulated. Once we're on the warm side of the HRV, if you will, we don't need to insulate them anymore. But on the exterior runs, we need to really insulate those. And I've seen a lot of projects in many climates where the exterior runs were insulated, but the insulation didn't have an air barrier. They weren't taped off properly. And essentially what happens is if it's running through within the thermal envelope and it's freezing outside, we're bringing in freezing air from the outside. We've got warm, moist air inside. And so the warm, moist air hits maybe some steel on the ducting, condenses, that water condenses, wets the insulation, and then it just turns into a whole soggy mess. So insulation and air tightness on the exterior runs. There's other duct materials. We work with something that is an expanded polypropylene. And so it's an insulated duct clipped together, and we can run it quite long, quite a far run in a multifamily project, and it works. But we would like to keep those as short as possible and insulated as well as possible. And then as we're doing installation, we're measuring. It's always great to find somebody with a flow meter, start up the system before we drywall, make sure everything's working properly, and then we can close it up. Filtration has now become a really big thing. And we all know why. We're all experiencing kind of the fires and the effects of these. In California now, we have a minimum MERV 13 filter. The MERV 13 requirement seems to be spilling over to many other jurisdictions around. And we're finding conditions, I'm personally finding them myself, where I really want MERV 14, MERV 15. And we had a couple of weeks where our home in Olympia, Washington, had smoke for 2-3 weeks, something like that. And we had really good results with a HEPA filter that we added onto our distribution system. So a little exam here in multifamily design. So the old days of pressurized corridors, essentially multifamily exhaust air locations, kitchens and bathrooms, same thing. We pick up the air there. And we begin to pipe it out. Supply air locations in the old pressurized corridor days, we would supply the corridor. We'd try to convince that air to go underneath the door, get inside of the unit. So we got positive pressure in the corridor, negative pressure inside the unit, and we get some airflow through there. And that kind of works, except all the, we got negative flow, we've got positive flow, it's coming into the unit, but the bedrooms are usually on the other side of that whole transaction, and they just don't get any flow. And here's what happens. This is what happens with CO2, and why Passive House is firmly stated in comfort and health, and why we supply bedrooms. The farthest point is because there's numerous studies. I've got a few other slides and other presentations that look at 6 buildings in New England there a few years ago. But essentially, in an unventilated bedroom, when people go in, they close the door and they start sleeping and they start producing CO2, and there's no exchange rate because there's nothing to force an exchange rate. The CO2 rises easily to 2000 ppm. It can rise higher, and especially in buildings that have a good air barrier, and it's a cold climate, so the windows aren't always open. This is why we open windows when it's really cold outside, is because the effects of too much CO2 are really uncomfortable, and we do feel them. It's the same thing with classrooms and education applications. So again, supplying the areas where people live, especially in the bedrooms, creating the negative pressure zones and creating a distribution pathway. An example of this is a 1,200 square foot apartment with 3 bedrooms, couple of bathrooms. The PHPP has got a 30 cubic meter per person requirement, 0.3 air changes across the volumetric design. It's got a kitchen, and the kitchen's 60 cubic meter requirement, or 35 CFM continuous. It's got a bath. Baths are 40 cubic meter or 24 CFM continuous at boost rate, is where these are. a toilet partition or a powder room, if you will, 12 CFM continuous. Some codes will say that's, maybe a 20 CFM minimum. It's where we gotta kind of be mindful. A laundry closet, another 12 CFM. So we're wound up with, on the volumetric calculation, 108 or 64 CFM for people. So our supply flow requirement at 18 CFM is 72, higher still. But it's back to the fact that we've got a kitchen and a couple of bathrooms and a powder room and a laundry room. All of these are going to produce moisture. So we want to be able to manage that moisture with ventilation and maintain, not see the humidity climb up above 65%. So that's 82 CFM. 82 CFM becomes the design for this application. And then we just design that 82 CFM across the room. In passive houses, home runs are a really good way to do it. And a home run is where all the ducting comes back to the unit. There's a number of European manufacturers that offer solutions like this. This is the solution we're used to working with, where we're not asking a system to branch out into steel ducting and then break into difficult corners where it's hard to get the flow through, and then switching into ducting materials that have higher static pressure. And because really at the end, we need to balance and commission these systems. So we need systems that are simple, have good solid curving joints rather than these T joints or 90 degrees in an extreme fashion. Straight up passive house project. This is a real passive house project. And this is below the screen in the bottom of the picture is a Zender CA550 designing, it's supposed to put out around 200 CFM. And because it's a brilliant builder, this is a great team, there's just no room to actually put the ventilation system. And so that steel box in the middle is a cooling coil, heating and cooling coil. One of the first projects to say, hey, I'm gonna do the classic passive house and heat and cool through my ventilation air, but there's not enough room to actually do it. So that's an issue, and why we come back to it's so important to understand the strategy at the design stage and allow for these things to happen, because this is the classic ductopus, and we could not get this system to work properly just because there's just too much static pressure and not a clear pathway to get the flows out of the unit, divide them up, and get them where they want to go. So very difficult. Getting to exhaust hoods in kitchens. So I say it's under debate because for my first 8 years, it was really clear in my education on passive house that we could introduce this small kitchen exhaust. And I did this in a retrofit home that I lived in, and I was very, very comfortable in it. That we could pull the kitchen air out, we could use a recirculating hood, and the application was just fine at that point. And I still believe that's generally correct, but I'm learning more. And I'm saying it's under debate because there are just things that I haven't learned yet. LBNL has been doing a lot of research the last 2 and 3 years, really about the particulate matter, the effective capture rate of range hoods, and how effective charcoal filters are in actually picking up some of the things that we want to filter out of the cooktop. So I would say in a passive house, you certainly can create a building that works using ventilation air in a 36 CFM range, 8 feet away from a cooktop, something like that. And it's a fine condition to live in as far as we know. It's just kind of like the smoke outside that, we can kind of see it. We don't really know the effects, and we've got to have a lot of equipment to understand what the PM 2.5 levels are. Kind of the same thing in the kitchen. I'm just kind of holding out that conservative viewpoint from the fact that we can do this. It won't clog the ductwork. The HRV will like it just fine, and I like it just fine. I just really don't know what the small particulate count is, and that should probably be taken in consideration. I find there are some owners that, as they approach a design, they've already got their mind made up, or they feel very comfortable about having a ducted range hood, and if they want that, that makes sense to me. And as long as we get them into the best building that we can, that totally makes sense. In the end, as we design and we put all of these ventilation systems in, the way that we balance them is we adjust the end terminations. And that's how we get the airflow to show up in the room per the design. So commissioning and final balancing is very, very important. There are new products coming out that don't have a duct system. And these are designed for new construction, but also for retrofits. We do some workshops on a system like this, but this is essentially decentralized, so small spaces. There are ways to spread the ventilation out across these small spaces. It's demand driven. So it operates typically at a lower ventilation rate. And then as people come in, they create CO2, it sees the CO2 and then increases the ventilation rate to manage the CO2 at a certain level. They're super interesting. We're just getting started with these. And as we get into more larger buildings, it's the same as what we've really talked about. Commercial spaces, there's retrofits you can do by removing RTUs off the top of the building. These are two new construction full-on passive houses, and they're complete. They've been occupied by a number of years, just using the same strategies, placing units in the upper floors, ducting the units to the outside into small dog houses, if you will. On the top, separating the supply and the exhaust flow so they don't mix, dropping the interior flows into a series of risers and pushing those risers out into the units. Simple layouts. We're just stacking units across the building and using one common unit at the top of the building. And then the other strategy is to just look at a building and look at the unit and go suite by suite. Lots of buildings go suite by suite in the multifamily world. So little units would use something as small as the CA70 for a studio. And then larger units, 2 and 3 bedrooms, can use the CA200. And then there's, in this building, they ganged a bunch of studios across one face of the building and hooked them all up to CA550s, which would run comfortably 180 CFM to 200 CFM, and split that flow across all those units. And then high rises. High rises can be one large unit and central ducting and risers, or they can be suite by suite. There's a tower that we did recently with small CA160s. CA160s sweet spot is right around 50 to 60 CFM per unit. So it's great for a studio, 1 bedroom, something in that range, full on PHI rated, and easy to install in ceiling troughs and things like that. When we get to the end and we're starting these systems up, then the ventilation in a passive house is extremely important. It's the last phase that wants to be done by a qualified person. And essentially what we're going to do is we're going to show up at the building. We're going to measure the flow coming in and the flow going out. We'll adjust the equipment so the 2 flows are the same. That way we get the effectiveness that we're looking for. And then we'll go room to room and then push that flow. If we have too much supply flow in one room, we'll close that room up a little bit and at the termination and push that flow into another room. The units are getting better as we go. This is actually a retrofit that I did in my house right now. And that's a Q unit, and that's one of the first self-balancing units also, like the little one. So when I plug that one in and I start the commissioning wizard, which is kind of the 2 little pictures on my iPhone in the app, first thing it's going to do is ask me a bunch of questions. I answer the questions, and then it's going to balance its own flow. It's got its own onboard mass airflow meters, temperature meters, and an algorithm and programming to basically set the flow by itself. And then once the flow is set, it will then move into, and then I can, go to each room and kind of balance each room and get the flows showing up per the design I made. And then just a quick note, the flow is coming out of the unit, going into those large steel boxers, which are silencers to knock down the noise, because in a passive house, we've got to be super, super quiet. And then one box is longer than the other because that longer box has got a big filter where I can put an activated carbon filter or a MERV 14 filter, 15 filter, because I'm just seeing more and more smoke as it comes up. So now I can take a quick scan and help with some questions if I can. So we've got a few minutes left, so let's see how we do here. Okay, so here's a question from Ashley. Does the industry efficiency test both low and high outdoor air temperatures, or only testing for cold climates? Well, that's a great question. So the tests are based on cold climates. PHI developed another set of tests and another testing requirement for hot humid. So in the PHI database, for some of the equipment, some of the manufacturers have submitted their equipment to that testing for summer testing. But the industry is based on cold climate testing right now. And hot, humid, or warm is different than cold. And I don't fully understand it quite yet. So hopefully that's a helpful answer. Yeah, for sure. So Valentine made a helpful comment. Should be careful to make sure the fan motor is rated for the increased pressure drop from a HEPA filter. Otherwise, you can wear the motor out faster. Better units have better ECM motors. And here's a note: when we design projects to ventilate at the normal rate at about 60%, up to 60% of fan capacity. So we leave another 25 to 30% in boost rate. And that's a negotiable number. So the normal load, if you introduce extra filter, or if the filters become clogged, that definitely adds static, but we start with the low number. We never really work around designing, anything above 60% normal flows. And I looked at actually the static difference on the HEPA filter on my unit when we were using it. Actually, no, I didn't, because it was separated from the unit. So I was going to look at that, but I have not done that actually yet. George, a comment, kind of a question, or maybe it's a straight up question: how to protect the core and its effectiveness from oil while extracting air from the kitchen. So that is, in my understanding, that is down to the 8 feet away. In any direction, 8 feet, a straight 8-foot line away from the cooktop, because by then the oils are theoretically supposed to cool and fall and not really show up in the ventilation ducting. Additionally, the equipment that we sell on the Zender side, the exhaust grills have a pre-filter that is there at the termination, and so a filter can capture that, and the homeowner can actually change the filter. My concern is if they don't know about it and they don't change it, then we're back to the earlier question of adding static onto the system. So yeah, 8 feet away is a nice, safe number. I've never heard any challenges around that. Or size the HEPA filter, Dave, or size the HEPA filter correctly for low pressure drop in an external slot, for sure. definitely sizing it correctly. And HEPA filters, we're not as good as we'd like to be on HEPA filters and have all the possibilities. So yeah, that's a consideration, and I don't think we could spend too much time thinking about. I think we could spend lots of time thinking about that, and should spend lots of time thinking about that. Okay, so Ashley, comment maybe. I'm concerned about keeping as much contamination as possible out of the ducts, including the air intake, pulling dust from outside until it gets to the intake filter, and then you have dust in the cold duct, which concerns me a bit for mold if conditions are right. So really good point. Spent a lot of time thinking about this, and some of the strategies have been to put filters out near the building edge. So you'd have essentially two sets of filters, one all the way out to try to kind of knock down the amount of dust and contaminants that's coming in. And then there's the onboard filter at the unit. And the onboard filter at the unit is now going to be a MERV 13 because that's really the requirement, certainly in California. I don't like the two filter situation because I've seen too many of them get clogged, throws the system out of balance, adds static to the system. And really the MERV 13 filter, if we're doing this right, it's changed every 3 to 5 months, maybe at the worst twice a year, because they really do get clogged, and we're really aware of how much that is. And they're sized appropriately for the flow, so they don't create a lot of static. But then when we add another one on, and if it's not maintained, that's a problem. So far, I haven't seen anything bad show up or develop in the exterior ducting. Generally, they remain clean. The air is always moving. And so we don't see a lot of things building up on that. It certainly bears inspection. And I think the important point that I've landed on for the systems that I work with is no 1/4-inch mesh or 8-inch mesh at the exterior hood, full on 1/2-inch mesh, because we really want everything to show up and get caught by that filter right before the core at the unit, and change it regularly. And that way, when we forget to look at the building edge and the collection, it's not really such a concern. Comment from George: cooking with gas produces more toxins and particulates like benzene. That's for sure. That's the thing that we've learned more recently, or it's been talked about more recently. And I just recognize I don't think there's a final word on that yet. I think there's more that we're thinking about. And it's really pertinent for municipalities that are doing multifamily and multifamily passive house, because they're really relying on the ventilation system to pick up the kitchen exhaust. It's a great strategy, but we really need to understand how well it's working, and more measurement is needed. Valentine: typically don't install gas stoves in a passive house since you will need makeup air supply for the combustion. Recommend induction stoves if possible. For sure, done it twice. Did full on, I did a retrofit, and so I actually got the retrofit down to 1 air change an hour. And it was a piece of crap 70s building, should have tore it down, but we retrofitted it, got it down to 1 air change, did an induction, 30 CFM, 32 CFM kitchen exhaust, and a charcoal filter range hood. It worked great. Yet when we're cooking, I think with induction, we still have the potential of creating some harmful fumes, and we don't really know about that much. So I'm totally with you, and definite induction. Just did another one, but still want to think about kind of what's coming off that stovetop. Does the equipment monitor state of the filters and put on a warning light, or send info to the app when it needs to be changed? Perhaps even giving a qualified number of days of filter time left. So that from Paul, and yes, so that's a yes, that's a qualified yes. So the app tells me on my home, I get a warning showing up on my phone saying, hey, get ready to change your filters. It's a clock counter. It's not a device that's looking at static pressure and trying to tell me that the filters have developed and become clogged and it's built the static pressure up. So that's working on that one, and it's fine, it's reliable. So I just go down, change the filters, and away to go. That other little unit, the Fresh R, actually has it. It's why you can't really talk about it too deeply today. It has a whole bunch of onboard information, and it has the potential to lift that information up to the cloud and then back to you in a way that's accessible. And it will actually tell you when static increases. It will tell you a whole lot of information. And so it's the closest thing right now that will actually tell you kind of what the condition of your equipment is in. And from that, you can also kind of look at the filter condition. So, John, thank you. I've used up almost all of our 90 minutes. I need to leave you a couple minutes to say thank you and all the wonderful things about 3C Ren, which we really appreciate. And a thank you from Ashley, really great comments and responses. Thank you. If you have any data on passive house bedroom CO2 measurements and any chance you have humidity measurements in a California coast passive house, I would love to see that. Yeah, an email to me is fine. I'm just Albert at smallplanetsupply.com. And the CO2 measurements in a passive house are going to be pretty boring. It's going to be pretty Maytaggy, because they're generally designed well. There's data available. I don't know that I'm tracking it that well, because every time I look at it, CO2 is just great. All the conditions are great. Humidity measurements, many projects have not done humidity perfectly, and I'll have to think if we know about that data and where the best place is. So with that, maybe back to you, Sean, with a whopping 2 minutes left.
Sure. Thank you, Albert. Great presentation. So much interesting content. I'm going to be thinking about ventilation in my building here all day now. And thank you all for the really engaging and wonderful questions. Appreciate that as well. I'll keep it super short here. So we do have AIA units available for this course. Unfortunately, we don't have ICC units right now, but we do have AAA. So if you entered those during registration, entered your number, I can get those out to you. If you have any questions about that or not sure if you provided your information, feel free to email me directly. Albert, I'll reach out to you to get a copy of the slide deck, and then we'll go ahead and share that with everyone who attended today in case you need to reference something or take another look at some of the slides. We do have a variety of upcoming courses. Encourage you to check those out on our website, on our live events calendar. The one I will note is if you are in the Central Coast area, on November 9th, we will have our next regional forum. I mentioned that earlier. We'll be talking about energy code, climate policies, and funding coming down towards our way and how to make the best use of that. I'll also just pop in Albert's email here and the Small Planet Supply website, so you can check those out. But yeah, just want to thank y'all for joining today. Really appreciate it, and great presentation, Albert. Look forward to hearing more about ventilation in the future.
Great, thank you. Really appreciate everybody's time today.
All right, and with that, I'll let y'all go. Thanks for joining us and have a great rest of your day. Bye, everyone.